Hello, my good friends. This is Dr. Mohammed Nizami again with another microwave and RF radio frequency device designs and 3D modeling. For the last three videos that I have presented, we covered basically the concept of crossovers, and we classify them as being either a standalone package device that you could purchase or design and embed in your board that utilizes via transitions, or other types, which I'm going to talk about today, which is the last presentation in this series. I may have but one more, but eventually, we'll leave that to the coming months. So let's just refresh your memories. Okay, now again, Dr. Mohammed Nizami, RF and microwave circuit design consultant. I'm at your service if you have a need to offload and offshore any designs from North America or Europe. I'm available. You could reach me at this here or at this. I design transceiver circuits, board level circuits at this moment, anywhere between DC to 32 gigahertz. Okay, I also have a professional training. This is a training that is targeting practicing engineers and graduate students. It requires that you have some knowledge and background and experience previously with RF and microwave theory. The coming session will be on a 3-day hands-on RF and microwave device and 3D modeling using HFSS. These are basically going to be the training on the videos. If you log in and see my playlist and all the videos in there, basically everything that is covered in these 30 or so videos is going to be covered in these 3 days. So there are other two trainings on cadence and ADS design systems, or the pathway design suit, RF Pro, Momentum, ADS, which I will announce later. So if you decide to come to this, please email me or give me a call, and we can talk about how to register you on this. It should be coming either the middle of this month if the number has reached the number that we wanted, or we will postpone it a month or two later toward the spring. So today, my friends, this is the fourth part of a series on RF to RF signal crossovers. Okay, and we define those. Please refer back to my videos for this theory. We started way back from defining a microstrip type via transition as a jumper or as a crossover, and then we went on to other crossovers that utilize multi-layers and the zigzag in between top and sublayer and bottom, transitioning from strip line to microstrip line and back to strip line and so forth. And then we covered one packaged crossover, and today we're going to be covering multi-channel filtering crossover. And this is basically the idea of this, is that when people looked at crossovers, they said, wait a minute, this thing is really can be converted into a resonator, and therefore it will have some frequency selectivity response to it, and therefore we can include in the crossover a filter. And then eventually when they stack this more and more, now and particularly for the SIW, okay, and in fact this is, let me put that in here, RF to RF substrate integrated waveguide. This is what we really want to cover. It has to be based on substrate integrated waveguide signal waveguide. Okay, so when people looked at this, they realized for a resonator with the SIW, if it's a square, then you can have two dual mode, where you can feed it on one side and get the other side, and then feed it orthogonally 90 degrees on the other side, and then get out on the other side. And they found out that you could actually, these things can be totally isolated, and therefore you can have them as a multiplexer of, if it's a square, it's the same frequency, whether you feed here or here, but one comes, they cross each other and they don't interfere, and they don't, there is isolation, high isolation. And then people soon realize that if you can make one side larger than the other side, which is a rectangular SIW resonator, then obviously you can have two frequencies. You can have different frequencies. You can have one frequency on here, another frequency in here, and they will cross over without any interference, even though they're two different frequencies, okay? Because simply you have one resonance which is associated with the length, and one resonance which is associated with the width. Okay, so you can have one lower and one higher depending on which side you feed, which one is the smaller, which one is the larger. Now, last time, you can refer back to my video, we designed this crossover, okay? And basically what it is, you've got a microstrip on top, and then you've got a microstrip on top that disappears using a via transition, back drilled via to a strip line and comes over, which was nice and neat. This device was beautiful. It operated anywhere from low frequencies to the sub 30 gigahertz. And this was done using a 6-layer board that we did it on RF3450B, I believe, and on 3440 pre-preg. And it worked beautiful. You can look at that video and see how this is designed. And then we designed another one. We went further and designed a packaged one, not to compete with the Zinger or the Anraen and the AVX crossover devices, off-the-shelf crossover devices, but we did this is the same, but except it's packaged now. It's a 3D package where a signal comes in through pads on the bottom, PCB pads, okay, and then travel to the top to propagate, to crossover, or to crossover from this side. And we showed all this design. Refer back to my previous video. This was it. And today, we're going to go further and say, okay, let's use SIWs. So conventionally, what people did is they needed a crossover with filtering functions. They would have a crossover here, just like the ones you saw, or eventually when they found they can do this with SIW resonators. And then, of course, you have two different filters, okay, with the filters on there, and you integrate them together. And of course, this is a traditional crossover cascaded with bandpass filter, okay. Now, this is large. There's likelihood of mismatching, inner mismatchings, and an additional loss. So eventually, people have realized that they could utilize the SIW crossover resonator itself as a filter, okay? And that's what we are going to look at today, which is a dual mode SIW cavity-based filtering crossover. Really, I should say dual mode multi-channel SIW cavity, because this assumes the dual mode assumes that you have a square resonator where it's the same frequency, except two different modes are propagating, which are orthogonal to each other, and therefore they can cross each other. The signal can cross each other transparently without any interfering. But if you make it a rectangular, then obviously you can have also a multi-channel. Okay. So let's just define further. So we need a dual channel. We're going to do a dual channel, dual mode, substrate integrated waveguide resonator cavity first, which is outlined in here. So what it is basically, it's an SIW line, except it has a feed line on the sides. Now, in my case, I just put in the feed line in there, regardless of the impedance. So I just attached the 50 ohm strip line to the middle of the SIW resonator. Obviously, that is not good because you need to do a little matching, and the little matching done. For those of you that remember from microstrip antennas, you can come in and you have a little inward slot that can control that can transform the 50 ohm to the low impedance of the resonator. But that's not the scope of our presentation today. But just look at this and say, this is a square or rectangular SIW with inputs on 4 sides. And what happens is we can design this such that the signal comes in here, goes over here, signal that comes in here, goes over here without any interference. So therefore, it's a crossover. And these frequencies, if it's a square resonator, they can be at the same frequency, because this will have the same resonance with 2 different modes. But if one is slightly longer than the other one or smaller, obviously then the resonance shifts for one mode than the other one. So we're going to realize the dual function integration of filtering and crossover in one device, which is this device, which will reduce complexity, size, cost, and signal transmission losses. The commonly used dual mode substrate integrated waveguide resonators operate orthogonally using these modes, okay? The TE201 and the TE102, which is M0N and M0N, with N and M as being 2 and 1. Okay, so 4 ports are arranged and the 2 signals are transmitted in these 2 modes, okay, respectively, which can realize the cross isolation of the signals. And that's what we're going to look at, okay? So how do we do this? Basically, we go back to the concept, and I did cover this in my videos on SIW filters. We start out with a cavity, a substrate integrated waveguide cavity with dimensions A and B, okay? And then we somehow come up with the resonance frequency as a function of these dimensions, not these dimensions, but the dimensions that correspond to what we call is effective A and B. Remember back from the SIW filter presentation, the way we design these resonators, SIW resonators, is that we make them similar in concept to a dielectric field waveguide with A to B dimensions. And so for that, for the comparison to be valid and utilize the equations that are for waveguides, rectangular waveguides, what we do is we come in and figure out what do we have to do to make this look like exactly an A and a B. So there is a little factor that you add in there, and that factor has to do with the ratio of the diameter of these vias, these wall vias, to the spacing between them, okay? And these are the 2 coefficients in here. So that's how this is deviated from the physical A and B for the SIW, okay? All right, so let's go ahead and look at this design, okay? And then, of course, now how do you, obviously, so at the beginning, you would want the A to be the A and B to start with. You want the A, B, and the diameter and the spacing between the vias, which is P in this case. So these are known equations, and we have covered them in the SIW filter. We know that D is usually chosen as the substrate waveguide length, wavelength divided by 5. So it's about 20% of the wavelength in the substrate. And then the P is basically, we assume it's twice the diameter, this distance between the center to center separation of the vias. We assume it's about twice the diameter of the via, okay? And of course, the cutoff frequency, you can find that out automatically just to verify that this waveguide can be usable at the frequencies, desired frequencies. And then we can find the W effective and length effective, which are here, basically it's the same equation as these ones here. Okay, so Once we do that, we have to come in and verify that the waveguide is operating appropriately. And as an example, today I use the Rogers 602, 6002 substrate, and I created this here, which was designed, and then we calculated the 50 ohm impedance for this substrate with 0.51 millimeter or 20 mil thick substrate. Okay, so the first design, which we're going to cover today, and I will show you in a minute on the in the HFSS, is basically 16 by 16 millimeter resonator. Okay, and it's got inputs right in the middle. These are designed as microstrip lines, and we ran this, and I got the resonance at 12.125. So, and then, so as you can see here, the frequency response from one end to the other is the same as the other of this side to this side, because it's a square resonator. So it's going to resonate on both sides, two different, same frequency, but different propagation mode. And in a minute, I will show you the, basically, here's what happens when you excite it with signals, is that one signal, one mode, you can propagate to this side, while this side is isolated as far as the signal that comes in here or here. Likewise, when you excite it on this side, it goes over and crosses over to the next, to the opposite side, while the adjacent inputs and outputs are isolated. Okay, and if you excite both together, this is the superposition of the signal, how it looks like. So let's look at that. Okay, so here is the okay, let's just make sure this is same one. Okay, so this is right now one of them. Okay, let me just get rid of this. So what we have the bottom, we have cover the bottom. Let me just so you can see it. Okay, so we've got the bottom is all ground. This is a single layer. Okay, Rogers 6002. And what I've got basically is I've got these square patch on top. Okay, that's the top right here, and it is basically surrounded by vias, and the vias are cleared right where the input and output to these sides. Okay, and when we run this, we get basically the signal is the resonator is running right now at this frequency, 12.125 gigahertz. Okay, the isolation between the two is in the 40 dBs. Okay, and if you look at the E field now, let's excite one side. Okay, so let's go 1 to 2 first. So coming in here, and we're gonna go, let's say this is 1 is excited and this is good. So we have this. So this is what we have. Okay, when we go from side 1 to 2, the signal propagates to the other side. So we have 1 is on this side and 2 is on this side. And when we do that, we get this E field distribution in the top conductor. Okay. Now realize that along the orthogonal other two input and outputs, the E field is completely zero. Okay, and that's the beauty of this thing. Now, likewise, if you go the other way around, so let's just go and say we're going to excite, we're going to kill this signal in here, we're going to excite the other side, and you can see that it went like this. So basically, we went from this to this. You can see like, and it does that to the other side. Now there are, in the literature, you will see some people put in vias somewhere around here, and there are some purposes where you can do that, so you can play around with the resonances and their placement and so forth. But again, the two modes are the same frequency except different modes. Okay, so we've got one mode. If you feed the signal from here, it propagates to here, and it doesn't interface, nothing comes into this port or this port. These are isolated. Likewise, if you put the signal on this side, you get out of this side, while these two are isolated. Okay, so therefore, this is a dual mode, because obviously there are two modes, the 102 and 201, and then same frequency, single frequency crossover, filtering crossover. Why filtering? Because obviously you can see here that the frequency response, it has a frequency response that is a single signal. Now, so this works good for like a CW or narrowband signal, but what would you do with a signal that is broadband? Of course, well, what we do is like you design a filter. Now, you wouldn't design a filter with a single resonator, like this one is a single resonator, of course. This is good for CW, maybe passing two different LOs to one point or the other, like for radar applications where it's a CW, single frequency, or narrowband modulated signal. But for signals that are wider in bandwidth, what we do is we will cascade more of these, and then that's where it's actually a complete SIW filtering crossover, which with a shape. And those they exist in the literature. You can look at Google filtering crossover substrate integrated waveguide designs, and you will see those. Okay. So, okay, so now, and of course, let me just show you, I did one slide. This is one slide. I took this from the internet. Oops. Let's skip over the next. Okay, so here is a filter. And this filter basically is a nice filter. You can see that this would be in what we just designed, which is the square batch or rectangular batch that I'm a resonator. And then of course you cascade, you stack more of these, and you get a nice frequency response with this. So like you can see in here, one signal you feed in here comes in here, while on the other side you come in here, feed in here, and these are two isolated. And same thing in here. These are two isolated. This is a true example of a filter and crossover construction. Okay, let's go to the other application that we have, the application example. So let's cover that. So what we did is we can come in here and say, okay, well, let's deviate the one of the sides a little bit, so we can get a resonance to move, a second resonance to move, and that would be dual channel in this case. Okay, and that's basically what we did. And when we sweep it in frequency, you get basically these two, depending on which one is larger. So the larger one, the longer one, that's lower frequency, where the narrower and smaller one is the higher frequency, of course. And likewise, if you look at the E field in the substrate, you get this pattern, which shows you that the signal is completely isolated. Okay, and likewise, when you look at the E field in the conductor on top, you can see that they're totally orthogonal and separated. So let's see that live. So what we have, okay, this guy here. So let's get rid of the E field for right now. So this is the substrate that we have right now. So basically the bottom is all copper. Okay, so we've got copper in here, and we got the placement of these vias all around, okay, based on the equations. And then we've got a certain effective width and effective height, or effective width and length that correspond, that are slightly like 1 millimeter apart. And then this is what we get when we sweep them. We got one resonance is here at 10.65 gigahertz, and another resonance is down at 10 gigahertz. Okay, so in this case, this would be a right one. Yeah. Okay. Oh, why does it come back? Always keeps coming back with the field. Okay, so this would be the dual channel case, and the likewise the frequencies is separated less, and if you look at the isolation is in the 40s of dB, as you can see here. This is the sweeping the signal from 1 to 4, which are the orthogonal ports. So 1 to 4 in this case. 1, 2, 3, 4. Okay, so let's look at the E field, and so the isolation is very good in this case. So let's look at this here and see which one are we here. So we're coming in here, and let's see this port. This port number is, okay, so this is 1. This is port 1. And in this case, I didn't have a sheet to excite the wave. This one is a wave port, not a lumped port like the other case. So we have in here, so let's see what happened when I excite. Okay, so I'm exciting both of them now. So let's make sure that there's only one. Okay, so this is the first one. Okay, you can see the signal coming from here, going out here, and these are isolated. Okay, now let's excite the other one. So we want to zero this and put full power on this. And now we've got the signal on this side. And the color is a slight difference, and I'll show you why in a minute. So let's just show you this in action. So we've got this, okay, which has higher amplitude in these areas right here than the other one. So the other one is orthogonal to it. And the reason for the fact one of them is stronger than the other one is obviously from the amplitude. You can see the amplitude is not equal for both. One is minus 2.5, and one is almost 2 dBs, while the other one, the previous design, this one here, the signal strength on both of them was the same. So you get the same color on both of them. So whether you're on this side or this side, you can see that you end up with both. Okay, so now we've done this, and so this is a multi-mode, multi-channel substrate integrated waveguide crossover. So where would you use this? And I made a little sketch here. I borrowed this from IEEE in here. This is a design, a filter design, which has in it 6 filters. Okay, 1 filter here, 1 filter here, 1 filter here, 1 here, 1 here, 1 here, and they're all orthogonal to each other. Okay, so you could come in and choose any of these signals, and this is the one that I just did. So one could do is you could actually have a signal that comes in and switch over between whether you want to go this way or this way. Okay, and then go out and then combine the signal again. So this is really a two-way dual filter. in the sense, or it's the other way around. You can come in here and go that way. Same thing in here. Now you can go in, and obviously you can go into any one of the 6 different filters to go out here, or from here, coming from here, and then go out and choose to go into any of these 6 banks of filters. So it's a filter bank, basically. For those of you that may from DSP, FFT filter banks, this is a filter bank implemented. And where would you use this? You can use this in transmitter on the receiver, in RF signal routing, and so forth. There's many applications for this, and EW and communications to provide different bandwidths, different filtering to avoid jamming, interference, or whatever. Okay. So, ladies and gentlemen, you have it. So I hope you enjoyed this. Again, if you like what you see, you can register for, contact me to register for my training, hands-on training. And if you have any need for, I currently a few projects with the clients in Europe and in North America. So if you have any design projects, I can always, I still have capacity, bandwidth to provide my services. My rates are very reasonable. I operate out of Jordan, so it's much cheaper than to operate in the United States or Europe. And so you'd be surprised. So if you have a certain project that you want an RF engineer to work on remotely, let me know. I travel occasionally for testing and critical meetings, but please go ahead and reach me out at this number or this email. Again, this is Dr. Mohammed Nizami. I hope you have enjoyed my lectures. I may have few coming lectures on using ANSYS HFSS, but I'm going to turn over now to more of the active and system level designs using system view and path wave suits of RF Pro and momentum and ADS. So hopefully I may have, it depends. So we'll see. We'll see you on the next video, whatever that concept is. Thank you very much and have a great day.